going to be talking about my false presentation, which is the topic of deep learning for exoplanet detection and characterization from Starshade images. My name is Zahra Ahmed, advisor is Professor D'Amico, and this research has been in collaboration with some folks over at JPL in the Exoplanet program, so Renu Ha and Mario Damiano. So this work is centered around image processing, but I'm going to spend some time putting it in context of the bigger picture with the background and motivation. Then we'll discuss the state of the art, the approach that we're using in this work, and showing the results and some of the limitations of that work. And then we'll end with some conclusions and zoom back out to talk about how this work will be extended over the course of my PhD with future work. So the past 2 decades have seen kind of a proliferation of exoplanet discoveries, primarily through indirect imaging methods, where we infer the existence of an exoplanet based on its effect on the host star. This only provides us with limited information about the planet beyond its existence. So in the Astro 2020 Decadal Survey, it was determined that kind of the overarching goal for this next decade of exoplanet science is going to be even more ambitious, and that is to discover and characterize Earth-like planets that are capable of supporting life. So in order to achieve this goal, we need to switch from indirect imaging methods to direct imaging. So to achieve this goal of direct imaging, we then need very advanced direct imaging missions. And so in order to achieve the goal of atmospheric and spectral characterization, our direct imaging technology needs to be more advanced than it has been to date. And underpinning the success of these direct imaging missions is the ability to analyze and interpret the resulting data. And being able to analyze the data is critical both for the development of these missions in terms of design validation, requirement setting, as well as for the deployment. So in terms of data management and eventually payload autonomy. So we'll discuss soon that we don't currently have the infrastructure to meet the demands of these direct imaging missions. But before we go into the state of the art, we want to narrow in the scope of what types of technologies we're talking about for direct imaging. So the motivating example for this work is going to be starshades. Starshades are a starlight suppression technology that can be used in conjunction with a space or ground-based telescope, and they're used to increase the contrast ratio between the star and the planet, which is very important for direct images because the star is orders of magnitude brighter than the planets themselves. So starshades are an alternative to coronagraphs, which have been used more commonly because they're easier to implement. But recent studies and recent starshade mission concepts have indicated that starshades would be able to increase the contrast ratio beyond what coronagraphs are able to perform. And so they're a perfect example of an advanced direct imaging technology that has the potential to help us meet our goals of characterizing habitable worlds, but that where image processing algorithms are kind of critical to the development. And this is most easily communicated if we look at some representative images from these starshades. So there are several sources of noise in all direct images, and these are kind of specific to starshade images. So we have astrophysical noise from exozodiacal dust and scattered starlight. We have sensor noise, we have instrument noise from the starshade, from the telescope, from the formation flying misalignments of the two. And all of these sources of noise are spatially and temporally variant, which produces really low signal to noise ratio images that are very difficult to calibrate. So in these scenarios, on the left, this image has, I think, 2 exoplanet signals in it. And on the right, we also have 2 exoplanet signals. And so clearly, just from visual inspection, we cannot determine where those planets are unless you are, have better than 20/20 vision, maybe. Oh, so actually I was incorrect. So there's actually 3 images, 3 exoplanets on the image on the right, which I guess further proves the point that these images are very, I can ask the audience, yeah, which is very difficult to calibrate. So the red squares show where the planets are. I've also kind of annotated some of the sources of noise that are most visible in these images. So the exozodiacal dust kind of creates that graininess that you're seeing, and the light from the host star is obviously kind of washing out the planet signals. So the bottom line here is that we need image processing algorithms to make the data interpretable. So we've additionally kind of discussed that these algorithms need to be efficient and robust to meet the demands of these direct imaging missions. And we've shown that without these image processing algorithms, we can't really conduct meaningful analysis on the resulting data. So now we can move on to kind of state of the art. And the state of the art can be categorized into two main categories. So we have background subtraction pipelines, and we have supervised machine learning. So just a high-level overview of these two before we discuss specific algorithms. So for background subtraction pipelines, there's two main steps. So the first step is background estimation, where we generate a low-rank approximation of our data that we can subtract off from the initial input image to reveal hopefully the residual exoplanet signals, and then some type of source detection, commonly visual inspection. So the residual images are commonly visually inspected to determine where the exoplanet signals are, but there are a few algorithms that do this as well. On the supervised machine learning side, we're going to focus specifically on convolutional neural networks. And the idea here is that the convolutional neural network, or the supervised machine learning algorithm, learns the features and patterns in the data set through the use of sequential filters that are updated through an iterative training process. And this relies on having data that is labeled so that we can supervise the learning, which is where that name comes from. So diving into the background subtraction pipelines. So in the background estimation category, this is where most of the innovation has been in the recent years for this type of algorithm. So we have principal component-based algorithms, which use principal component analysis to determine that low rank approximation. Alternatively, Loki and LLSG both do local optimization on different parts of the image and then combine them to create the image that's subtracted off from the inputs. And like I mentioned earlier, once you have those residual images, you're either visually inspecting to determine where the exoplanets are, or you can use some of these source detection algorithms. The two main ones are Andromeda, which uses a generalized maximum likelihood approach, which uses a maximum likelihood approach. And then we have the GLRT, which is the only Starshade specific source detection algorithm, and that uses the generalized likelihood ratio test. So a few things to note on these background subtraction pipelines is that they are very prone to over subtraction because you're creating a low rank approximation. It is very likely that you are actually going to include the exoplanet signals in those approximations and subtract off the signal from the residual image. They are also primarily used in conjunction with differential imaging. So the images have to be calibrated using differential imaging, where you take the same scene from multiple roll angles or at multiple wavelengths in order to obtain that low rank approximation. And this is very limiting for space-based telescopes because obtaining multiple calibration images for every scene is very expensive. And even more so with Starshades when you have to account for the rendezvous operations of the Starshade and the telescope. The advantages, though, are that they are pretty simple and effective when they work, and they are very interpretable. You can, analyze the data, you can look at the individual components and understand how it's relating to the physics. On the other hand, we have supervised machine learning. And so supervised machine learning, specifically CNNs, have been applied extensively and successfully in a lot of related fields. A few to note is radio astronomy, which is very similar to exoplanet detection, spacecraft pose estimation, which we have a lot of experience with in SLAB, as well as agriculture monitoring using machine learning. In terms of exoplanet detection, supervised machine learning has been very limited due to the lack of data. So the two main approaches, or the two main pieces of literature that have used machine learning for direct imaging, one was focused on the generative adversarial networks to actually generate more training images, less so on the detection algorithm. And the other was using CNNs for high contrast imaging sequences. So again, we're then tied to having calibration imaging sequences instead of being able to make detections on single images. And so CNNs basically, they present a very efficient alternative to these background subtraction pipelines, but they've had limited applications due to lack of data. So, when we're speaking of lack of data, the difficulty, of course, with real data is that we don't know whether the images that we currently have contain planet signals. And with starshades, we don't actually have any data. Luckily, there's been recent advancements in simulation technology with the Starshade Imaging Toolkit for Exoplanet Reconnaissance, or SISTER, which is able to simulate starshades with several sources of noise. So this is the most realistic simulation technology we have in order to generate synthetic starshade images. The challenges with SISTER, and this will come up later when we discuss the data set we used for our work, is that it requires extensive domain knowledge in order to create physically realizable simulations. And it is quite computationally expensive to generate these images. But the bottom line here is that SISTER enables the generation of synthetic starshade images, which we can then use to train a CNN. So kind of to summarize what we've discussed, our high-level objective, again, is to characterize habitable worlds. And we've narrowed in this scope to a more tractable problem of focusing on starshade missions. So we can kind of state our objective as enabling starshade mission concepts by developing robust and efficient image processing algorithms. The opportunity that we have that enables this research right now is that we can leverage advancements in supervised machine learning, as well as in starshade simulation software, to develop data sets that we can then use for our novel approach, which is to develop and train convolutional neural networks for exoplanet detection and characterization. So the approach and the results that I'm going to discuss right now are going to be focused on the detection part of this problem. And then we're going to discuss how we can extend this approach to characterization with future work and with the rest of my PhD. So before we go into the architecture, we need to discuss the actual data that we're using and the features of this data that we should be using to inform our CNN architecture. So we're using a synthetic starshade data set that was generated by JPL using SISTER for their Starshade Exoplanet Data Challenge. And essentially, they have 20 unique exoplanet scenarios, so 10 systems with 2 visits each. And then there's varying levels of noise and intensity for all of those images, which is what generates those 1440 images. There's a few key things we need to address with this data set. So first, everything highlighted in red is what we need to make sure that we're addressing with our architecture. So 1400 images is quite small for a machine learning algorithm, so that's something that we need to be aware of with our architecture. The images are quite small themselves. They're only 64 by 64 pixels. There's a varying number of planets per image, so we can't be prescriptive with how many detections we're going to make. And then the images on the right show that the planet signals, as we saw earlier as well, are quite small. So we're actually going to treat them as point sources for the current work. So now when we get into the convolutional neural network design, I'm going to discuss in depth a little bit the 2 labeled parts, so the actual model itself, as well as the loss function. And then I'll provide an overview of the rest of the model and training parameters that we used. So going into the model. So we are using the UNet architecture, which was originally created for biomedical image segmentation. But the reason that it's chosen for this particular application is because, as you can see, it has an encoding and decoding part of the network, and the output is the same size as the input. And so it gives us a one-to-one mapping between our output and our input image. And the reason that that's important here is because in the encoding part of the network, or the downsampling part of the network, we're learning to extract features from larger regions and capture some of those more abstract features. And then when we decode and get back to the original input size, we're able to recover some of that spatial information that was lost during downsampling, which allows us to have a little bit more precision with our segmentation, which is important here because our signals are so small. So we need that precision. The other benefit of using this model is that it's quite small. It's 6.2 million trainable parameters, which is relatively small for a CNN. And this is important because, again, since we're using a small data set, having fewer parameters helps prevent a little bit of overfitting. So the main modifications that we made to this UNet architecture is, one, decreasing the size of it. So because the input is the same size as the output, it's prescriptive with the minimum input size. So we reduced the amount of downsampling layers in the network in order to accommodate our small images. And the other modification we made is to the detection head. So typically the output of this network is just the pixel-wise probability of whether or not each pixel contains the object that you're interested in. We've altered the detection head to actually regress the probability as well as an XY location for each pixel. So moving on to the loss function. So the main takeaway with the loss function, without getting bogged down in all of the math, is that there are two parts of the loss function. So I mentioned that the output of our CNN gives us a probability and an XY location for the predictions. And so the focal loss is addressing the confidence. So we want to drive the confidence of our predictions to 0 if there's not actually a planet there, and we want to drive the confidence of our predictions to 1 if there is a planet there. And so that's what the focal loss is doing. And then for the regression loss, we're just using simple mean squared error. So the training details and metrics, we're using k-fold cross-validation here. So we'll share the results of that in a second. A small batch size. We're using the atom optimizer, which is a extension of stochastic gradient descent, as well as we're including data augmentation. It's limited right now, but we're using flips, rotations, and crops. And this is, again, to help address that small data set that we are working with. The metrics that we're going to be using to evaluate our performance is precision, recall, and the L2 error of our regressed locations. The thing to note with precision and recall is TP stands for true positive and FP stands for false positive. This equation's wrong. Okay, but we'll fix that. So the precision basically tells us of the detections you made, how often were you accurate? And the recall tells us how many of the true signals did you capture? So these are the results from our k-fold cross-validation. So we have each of the folds listed here, but the main takeaway here is that overall we're doing very well. We're getting 90% around precision and recall with an average error of around half a pixel. And you can see that the standard deviation between all of these folds is quite low, so around 1%, 2% for all of our for the precision and the recall, which I guess indicates that our data set, I guess there's several things that this could indicate. It could indicate that our data set is very homogeneous. It could also indicate that we're overfitting. And so these are kind of limitations that will need to be addressed, but overall it shows that there's no outliers in our data set. So more visual representations of the results. So we have the input images up top, and we have the output images with annotations for the predictions and the ground truth on the bottom. A few notes here. So again, remember these images are 64 by 64. So they're quite small, and the annotations for both the circles and the boxes that we're showing, those are 2 pixels width. So this is obviously blown up for the sake of showing it, but the actual scale of this is quite small. So here are, predictions where we're doing pretty well. We predicted both or all of the exoplanet signals within, a decent amount of distance. But there are some failure cases. And so looking at some of these images, so we have, on the left, we have the CNN overpredicting, where we have many more predictions than actual exoplanet signals. And on the right, it didn't predict anything, right? And so kind of we need to start thinking about where those failure cases are and how that plays into the architecture and the training that we are conducting. So moving on to comparison to the state of the art. Also, you're going to see some to-dos on the next few slides. So comparison to state of the art. So we're comparing to 2 principal component-based algorithms, background subtraction methods. So the first is PyClip, which is it's a Python library that implements the CLIP algorithm, which is one of the most predominant PCA-based estimation algorithms. And then we're also comparing it to the results from the Starshade Exoplanet Data Challenge. And the main, participant in the data challenge used a principal component-based algorithm as well as a full pipeline. So I think I have notes on that. So he used principal component analysis to estimate the background, then used match filtering to filter those residual images, then used local maxima detection to find the regions that are well matched to the point spread function, and then did outlier detection, and then thresholded. And so that's kind of his full pipeline. And so as you can imagine, that's quite intensive, and a lot of manual tuning and visual inspection is involved in all of those steps. So you can see we're outperforming both of these. A note here with PyClip is that this is kind of a naive approach in terms of this was me using PyClip without doing a ton of optimization of the parameters. So it was just kind of using the default PyClip scenarios. Okay, this is a to-do as well. So I'm going to show some out-of-distribution images. I'm generating some out-of-distribution images using Sister. So the limiting cases that I want to kind of qualitatively address here is what happens when the planets are far away from the host star, because if you saw in most of our images, the planets are kind of clustered pretty close to the host star. So planets far away from the host star, images with no planets at all. Right now, all of our images have at least 2 to 3 planets in them. So we need to address if there's no planets, which is going to be the case most of the time. How does our CNN perform in those scenarios? As well as looking at a noiseless image. So just seeing how does is the CNN able to automatically detect the exoplanets if there's no noise in the image? So a summary and some next steps for this portion. So summary of contributions that we've discussed so far. So we've leveraged advancements in supervised machine learning and synthetic images to develop a CNN for exoplanet detection. And we've compared the performance of this CNN to the state of the art with, the results indicating that our CNN can outperform PCA-based approaches, as well as, once that slide is finished, I'll have shown some preliminary qualitative analysis of the CNN's limitations to out-of-distribution images. The next steps for specifically this exoplanet detection part of this problem is, number one is to expand the training data set using Sister, as well as we want to have a more quantified sensitivity of the CNN to out-of-distribution images. And then finally, we've kind of discussed how the CNN and supervised machine learning can outperform some of these classical techniques, but they've been pretty effective for a while, and there's kind of opportunity for there to be some synergy with using principal component analysis or some of these background estimation techniques in conjunction with our CNN. So looking into how we can combine some of these state-of-the-art with our current approach. So moving on to future work. We focused on exoplanet detection, and now the future work is going to focus on the characterization part of this problem. So this is also a to-do. This is me starting to work through some of these problems, so I'll have this by quals, but it's kind of still preliminary. So I want to address how characterization can be encompassed by a lot of different problems. So we can, the simplest way is to, with the exoplanet detections, also detect the exoplanet star flux ratio. And we can use, segmentation to determine the flux and extent of that planet signal. So this is kind of transitioning from treating the planets as point sources to as extended sources and kind of quantifying the spread in the images. The other characterization is exozodiacal dust, which is not directly the exoplanet itself, but could help us with our exoplanet detection because it is one of the primary sources of noise. So if we use a multitask architecture to characterize the exozodiacal dust, that when used in conjunction with a detection head for exoplanets, could help improve the training process for both of those. And then the final, and this is kind of the holy grail for future work, is exoplanet spectra. So being able to either predict the parameter distributions of a spectra given direct images and integrated field spectrometric data. I'll work on that. And then this is also a to-do slide, I'm going to focus in on that spectral analysis. I've been working with Bruce McIntosh to kind of better understand this problem, and I'm hoping to present a little bit more of a fleshed out plan for how machine learning could be integrated into spectral analysis. As of right now, this is kind of just the main pipeline that is currently used. So the raw data from the direct images and the IFS is, turned into a data cube. So you can imagine for each, it's called a spaxel for each. So it's not a pixel, it's a spaxel. So for each spaxel, you have wavelength information. And so the idea is that you can take that data cube, detect where the exoplanets are, and then just for those regions, kind of flatten out the spectra that you have. The most computationally expensive part of this is hopefully where we can introduce machine learning, which is once you have those spectra, they use forward modeling to determine the characteristics of those exoplanets, in the sense that they have thousands of models of exoplanet spectra that they essentially compare to the data that they have, and then the best fit is what they use to characterize the exoplanet. And so, as you can imagine, generating those models, interpolating those models, and comparing those models is a quite computationally expensive process. So if we can integrate machine learning into this process to help go from the exoplanet spectra to a characterization of the planet, that could be an area for work there. I think that's all I have.